Hopefully you just saw in the last exploration that if you're given a function f of x and you add or subtract a constant value from that, it's going to shift the graph vertically by that many units. If your k is positive, the graph will shift up k units. If your graph is negative, the graph will shift down vertically k units. Hopefully you were able to obtain from the last exploration that when you add or subtract a value inside of the function, that you're actually doing what's called a horizontal shift. So you'll be shifting the graph. When that h was positive, the graph is going to shift to the right h units. Now, this is the part that's a little bit tricky because a lot of students would think, if I gave them this as an example, oh, your h is -2, it's not positive. Well, in this case, it actually is. Looking at this function, h is whatever value you're subtracting. So here we're subtracting just a +2. It's x minus +2. And then if your h is negative, the graph is going to shift left h units. And that would look like something like this. If we had x minus a -2, so in this case your h is negative, that would look like x plus 2. So it's really shifting the x values are really not that intuitive. With the vertical shifts, it was pretty obvious. You're adding a value, you move up, you're subtracting a value, you move it down. But with the x shifts here for like horizontally, a lot of students see this -2 and they think, oh, I'm going to subtract 2 from each x, so I'm going to move to the left, move in the negative direction. But in fact, you move to the right. So one of the things that I like to always tell students, and this is always an embarrassing thing, but think about kind of like your ex-boyfriend or ex-girlfriend. If you were in a room with them, you'd want to do the opposite. You'd want to be in the opposite side of the room. So always with the horizontal shifts and compressions, always do the opposite kind of what you intuitively would think to do. And we'll talk about that a little bit more when we do the putting it all together. In the last exploration, you should have seen that when you have a constant multiplied by your function, you're going to be creating either a vertical stretch or a vertical compression. If your a value is greater than 1, so if you're multiplying your function by a value that's larger than 1, then your graph will be a vertical stretch, or will be vertically stretched. If your a is between 0 and 1, then the graph will be vertically compressed. And furthermore, when you were exploring the value of a being less than 0, you hopefully saw that there was a combination of either a vertical stretch or compression combined with a vertical reflection, so it reflected it over the x-axis. In the last exploration, you should have seen that when you're multiplying a constant inside of the function to the variable, that you're going to be creating a horizontal stretch or a horizontal compression of the function. If that constant z value is greater than 1, the graph will be horizontally compressed. If that z value was between 0 and 1, then the graph will be horizontally stretched. And last, if it's less than 0, there's going to be a combination of a stretch or compression also combined with a horizontal reflection. In other words, you're going to also be having a reflection over the y-axis. Now we'll summarize all of our shifts and transformations. My best advice is to use this sheet as you're working through your homework and as a guide in studying for exams. It'll include everything that we've done in this section. Let's first start with vertical shifts. So if you're adding a value to the outside of your function and that value is positive, we're going to define k as being a positive value, you're going to shift the graph up k units. Now if you're taking your original function f of x and you're having to graph the new graph, what you'll do is you'll add k to each of your y values and your x values stay the same. Similarly, if you're subtracting k from each f of x value, you'll shift the graph down k units, and to change those coordinate points, you will subtract k from each y value, and your x values stay the same. For horizontal shifts, if you have f of x minus h, you're going to shift the graph to the right h units. To change those ordered pairs, you'll actually add h to each x value. Oops, add h, not x. Now remember, x's are not intuitive. You always want to do the opposite. So even though it says f of x minus h, when you change this and do your new ordered pairs and do your transformation, you actually add h to those x values. For f of x plus h, that shifts the graph to the left h units, and that actually subtracts h from each x value. Okay, compressions and stretches. So if we have an a value, a constant, multiplied to your f of x, that's going to be, if your a is larger than 1, it's going to be stretched vertically by a factor of a. If your a is between 0 and 1, the graph is compressed vertically by a factor of a. So your change to your ordered pair is you multiply each y value by a. So again, exactly what you'd think. Here this is taking a times f of x. So you take your y values, multiply them by a. Here you're adding k to your f of x. So take your y values and add k. So for the y's, you do exactly what it says. For the x values, so here when you've got a constant times the input values, you actually divide each x value by a. So you do the opposite. The graph is compressed horizontally if your a value is larger than 1, and your graph is stretched horizontally if it's between 0 and 1. And then for the reflections, if you have a negative sign in front of the f of x, that reflects it over the x-axis. Multiply each y value by -1. And if it's on the inside, that reflects it over the y-axis, and you multiply each x value by -1. Okay, so let's take all of these steps and put them into action. Why in the world would you ever want to learn about graph transformations? There's a couple of reasons. One, you're going to need them in trigonometry for graphing sine, cosine, and tangent functions. It makes your life a lot easier. So for the future, it'll really be helpful. But for now, it's even more helpful as well, because I don't know about you, but I don't want to have to do a table of values for that. And some of these get a lot uglier. So doing transformations actually makes it a lot easier if you don't have technology to graph things. Okay, so let's use all of what we just learned. Make sure you have that table out that we just covered in the last slide, and use those steps to graph graphs using transformations. So looking at this g of x, I can see that my parent function, you're going to always want to go back to the parent functions we learned in the last video. So the parent function that most closely resembles this is f of x equals x cubed. Now, what I usually tell students to do is to list out what the transformations are. Just like when you're creating a dish, like when you're making a meal, you follow a recipe. So you have steps that you follow to create this dish. We're going to create our steps for creating transformations. So let's create this recipe list, as I like to call it. So to graph g of x, the first thing that we'll do is we'll start with f of x equals x cubed. And now I list out the transformations. And the order, in fact, does somewhat matter. So when you're doing transformations, you always want to make sure that you do the reflections, stretches, and compressions first. And the order for those don't matter. And then the second thing you want to do after you've done those is then you'll do the horizontal and vertical shifts. And the order for those don't matter either. The reason that we need to make sure we're doing those in order is just the same reason that we follow PEMDAS. With all of what I listed in step 1, they're doing multiplication or division to the coordinate points. And in step 2, you're doing addition or subtraction. Okay, so the first thing we'll start with f of x equals x cubed. Now, what I see on here is, the first thing I see is this x minus 3, and that's dealing with the x values. So that's going to take the graph and shift it left 3 units. What that's going to do to my coordinate points is it's going to add 3 to my coordinate points. Excuse me, not shift it left, it'll shift it right 3 units. And again, remember with the x's, you always do the opposite. Okay, and the other thing that I see is this minus 3, and that's on the outside of the x cubed part. So that's going to be a vertical shift down 3 units. So that will take your y values and subtract 3 from them. So there's a couple different ways that you can go through this recipe. What some people do, and if you look in your book, you'll see your book does this, is they start by graphing this function, and then they graph the next one, the next transformation, where they shift it to the right, and then they do the last one where they shift it down. Personally, I think that can be a lot of work, and I don't want to have to do 3 graphs if I'm just looking for the end graph. So what I usually do is just take the coordinate points that are on those graphs and have them go through my recipe. So let's do that. So let's start with step 1, which was, I'm going to do it so they all are color coded, so I'll do it in purple, starting with the graph of f of x, which was y equals x cubed. So I'm going to put some points on there. Usually you want to transform at least 3 points. I usually say to transform 5 if you can. All right, so negative 2 cubed is negative 8, negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8. Okay, now we'll go through our first step, which was step 2, which was shifting it to the right 3 units, which was adding 3 to each x value. All right. So take each of my x values and add 3. Negative 2 plus 3 is positive 1. Negative 1 plus 3 is 2. 0 plus 3 is 3. 1 plus 3 is 4. And 2 plus 3 is 5. And my y values remain the same for that step. So you just copy those back down. Okay, now I'll do my step 3, which was subtracting 3 from my y values. So I'll write down the x values again, and we always do the most recent table. And now subtract 3 from each y value. Negative 8 minus 3 is negative 11. Negative 1 minus 3 is negative 4. 0 minus 3 is negative 3. 1 minus 3 is negative 2. And 8 minus 3 is 5. So now I have my points for my actual graph, and I can graph these. So at 1, I'm at negative 11. You can see this point moved down 3 and over 3, which is exactly what we said needed to happen. 2, I'm at negative 4. 3, I'm at negative 3. 4, I'm at negative 2. And at 5, I'm at positive 5. And again, we can look at this graph and you can see this is shifted. We're adding 3 to each x value and subtracting 3 from the y's. There's where that new point went. Adding 3 to the x's, subtracting 3 from the y's. Adding 3 to the x's, subtracting 3 to the y's. Okay, so that's how I usually do it. And if you do it this way, it's really easy for me also as the instructor for grading. Let's look at another example. Use the graph of f of x equals the square root of x to obtain the graph of g of x equals 1/2 times the square root of x plus 1. So you can see for g of x, it took f of x and we put it through some transformations. That parent function is the square root of x. So let's write out our recipe. Step 1. Start with y equals the square root of x. That's our parent function. You always state what the parent function is that you're starting with. Okay, step 2. First thing I'm going to deal with is this 1/2 because again, you always want to do any stretches or compressions first. So that is going to be a vertical compression, which means we're going to take our y values and multiply them by 1/2. Again, those are on the outside of the function. Whenever it's on the outside, it deals with the y values, and you always do exactly what is happening. So that's getting multiplied by the function, so we multiply our y values by 1/2. Step 3. Let's use purple for this guy. So here I'm adding 1 inside of the function. So that is going to be a horizontal shift to the left 1 unit, which means that you're going to take your x values and subtract 1 from them. All right, let's set up our table. So starting with the square root of x. When x is 0, the square root of 0 is 0. When x is 1, the square root of 1 is 1. I'm going to strategically pick some x values so that I get some pretty numbers. When x is 4, the square root of 4 is 2. When x is 9, the square root of 9 is 3. All right, so now let's move on to step 2. So step 2 was taking our y values and multiplying them by 1/2. So our x values stayed the same for step 2. All I'm doing is changing the y values. 0 times 1/2 is 0. 1 times 1/2 is 1/2. 2 times 1/2 is 1. And 3 times 1/2 is 3/2, or 1.5. Step 3. Take your x values and subtract 1. So this becomes -1, this becomes 0, this becomes 3, and 9 becomes 8. And then the y values stay the same. And now you can graph this. So we've got -1, 0, 0, 1/2, 3, 1, and 8, 3/2, which is all the way out here. Now let's look at a little more complicated one. Use the graph of f of x equals x squared to obtain the graph of g of x equals 3 times the quantity x minus 2 squared plus 1. In this case, we're going to end up having 3 different transformations: a vertical stretch, a horizontal shift, and a vertical shift. So let's start with our recipe. Step 1, we'll start with the parent function, which in this case they've told you what it is, but you can also look at the function and realize that it has to be f of x equals x squared. So start with, and I'm going to actually write it as y equals x squared. All right, step 2, let's deal with that 3. So that's going to be a vertical stretch of 3. All I look for on exams, just writing vertical stretch is enough for me. And then tell me what happens to the coordinates. So in this case, you're going to take your y coordinates and multiply them by 3. Okay, then we'll deal with this -2. So that's on the inside of the function, so that means that's going to affect the x values. So that's going to shift them right 2 units, which means you're going to take your x values and add 2. Again, with x's, you always do the opposite. And then our last part is adding 1, and that's on the outside of that x squared function, so we're going to shift it up 1 unit, which is taking your y values and adding 1. Okay, deep breaths, let's do this. So starting out with y equals x squared. So I'm going to do a couple of points that are on that graph from -2 up to 2. -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. All right, now we'll go through our next step. So we take our y values and multiply them by 3. So our x values remain the same. And we're going to take each y value and multiply them by 3. So 4 times 3 is 12. 1 times 3 is 3. 0 times 3 is 0. 1 times 3 is 3. And 4 times 3 is 12. Okay, now we'll do step 3, which is taking your x values and adding 2. So -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. And then our y values remain unchanged. And again, you always use the most recent table for the values. And then our last step, we're going to shift it up 1 unit, which is adding 1 to the y values. So the x values remain unchanged. And for each of the y values, I'm going to add 1. So that becomes 13, 4, 1, 4, and 13. So let's graph it. I'm going to actually graph it a little bit of a darker color. We'll do red. So 0, I'm at 13. At 1, I'm up at 4. At 2, I'm at 1. Oops. At 3, I'm up at 4. And then at 4, I'm up at 13. And there we go.